Alright, so as promised, here is the video I said I would send to you. So one quick note I want to mention is that I misspoke earlier. With Electron, with drawing groups, they are meta-directing, and with Electron donating groups, they are ortho-para-directing. So we basically just need to flip these two boxes. Make sure you have that straight because that's a pretty important concept. But other than that, let's move on and see what we can accomplish. So this is the very last question on the test. And it's kind of an involved problem. There are just a lot of little things that you need to look out for. Yeah, it is. It specifically is this question.
Oh, that's good. Thank you.
Okay. So we've got adipic acid, which has 1, 2, 3, 4, 5, 6 carbons in it. Adipic plus Alright. So the key component of this, as with all reactions, you do want to identify your nucleophile and your electrophile. The electrophile is over here. And this one will be your very adipic plus Alright. So the key component of this, as with all reactions, you do want to identify your nucleophile and your electrophile. The electrophile is over here. And this one will be your nucleophile.
That's because the carbon is like electron deficient.
Yeah. So if we consider the carbonyl group, let's just take this section right here and do a simple resonance structure. We pop that pair of electrons up, we get
alert from system UI server. Low battery.
O minus and carbon plus. So basically, either one of these two carbons those are the electron deficient, and they'll be the electron, let me write that in. Electron deficient. And this resonance structure we drew down here, I drew down here, helps to explain, oh yeah, there is a charge difference, positive to negative. And I don't remember what the pKa values are. You will need to use the pKa values at some point, not for like a not for a Bronsted protons transfer between two species, but you still probably want to brush up on those. Okay. So I see that that's the electrophile and that's the nucleophile. So what's most likely the nucleophilic part of my amine group? Well, yes, nitrogen, but the pair of electrons right there. So the first thing that's going to happen is we're gonna slip on right there. Carbon will have an expanded octet, so we'll just bring the pair of electrons up onto the oxygen. So really in the steps that follow, there will be multiple additions and rejections. So,
what is this reaction called? Like, is there some...
for this specific species, there's probably a name for it, but it's like nucleophilic addition dehydration.
It's just separate from the other ones we've been doing.
It's combining it's really a combination of things we've seen. So I'll label the steps as we go along. So this one right here is addition. That's the first step. And I'm just going to abbreviate the rest of this as R, so I don't have to keep writing it out. So we have this, and O minus, and the NH2, and then I'll just write that R group as well, plus. And by the way, this is happening on both sides. So we could take this pair of electrons on the nitrogen and have it attack over here, but we really only need to worry about what's happening with one group. So we have that, but the trick is we're somehow going to need to get a good leaving group out of this. Need a good leaving group. And we'll get that good leaving group from turning this OH group into OH2 plus. Or, what?
Can you explain what OH is that leaving group?
Well, if you bring that off, so if we did the elimination right now, we would get hydroxide. And that's a strong base. So strong bases generally do not make good leaving groups. We want to make a weak base. So
How do you add the H group?
that's where I'm getting to. So in this next step, we have to perform a proton transfer. And so this usually happens with... So in some chemistry textbooks actually show it as this pair of electrons going, aha, picking up that hydrogen, drops onto the nitrogen. What really happens, though, is we have an assisting acid species in there. So I'll take my A minus, which is just some generic conjugate base. That'll take this hydrogen right here from the nitrogen, then we'll drop it onto the nitrogen. So in the next step we get R O minus OH, and then NHR and HA. What happens next in the proton transfer times 2 is that this alcohol-like group will come pick up that proton, regenerating our conjugate base, and now we are ready to perform the elimination reaction, because now it's O plus H2 and HR. So this one right here, that was the second proton transfer. Yeah?
So if we were not given any kind of a conjugate base or anything, should we just go?
Wait, what? What happened? Okay, that was kind of random. Let me just pull it back up again. Now, where did we get to on this? Let's go back to over here. I think that should be good. How do I want to draw that? So replacing the hydroxide with the amine group and its carbon chain.
So, what do you want to see? The whole thing, both sides reacting?
No, you just write R. So in fact, it says specifically you may abbreviate if you wish to. And you probably want to do that or else you'll be drawing a lot of molecules. Yes, Brian?
Why did you bring up the whole salt thing?
Oh, the salt thing?
Is that simply just to explain the purification that goes back into this one?
Yeah.
So just verifies it's going back to the chain.
Mm-hmm.
Would that be something that would be important to know in the next few days?
No.
Okay.
Generally, for organic chemistry lab, it's a pretty big deal to generate salts and to extract them out of solution. And it's useful for general synthesis purposes, but for this test, just be like, it happens.
So for the test, just know this thing.
Basically. Yeah, what's your question?
Can you go to the step in blue again?
Oh, yeah, got distracted. So like I said earlier, you can either draw it as this OH just pulls off the hydrogen. In fact, that probably
The nitrogen?
yeah, pulls off the hydrogen from the nitrogen.
Okay.
And then, or we could look at it as some base just pulls off this hydrogen from ammonia or from ammonium derivative. So then the acid will pick up the proton, and then this hydroxyl-like group will just pick up that proton again.
So does it matter which way you look at it?
Not really, it's the same thing. Does that answer your question? Yes.
So if he gives us a conjugate base, we should do that. Whereas if he doesn't, don't worry about it.
Just be like,
pencil in a substitute conjugate base. But if you chose the conjugate bases, if not, just take it.
yeah. Like if you have a solvent in there, like ethanol, you should show HA as ethanol. ETOH. Luckily, this exam is only 150 points.
Just right there. Just go down. Perfect.
I've said specifically, like, what? No, he hasn't. Oh dear. I've looked at it and I'm like, I could do this pretty easily.
It's
I could-
open today, right?
Yeah, I could. I'm guessing I could probably do it in like an hour and a half. Right now,
You could, right?
I could.
So budget 4.5 hours.
By the way, get ready for some random musical inserts.
Tell him I won't take it until he sends out what each question is.
Oh, you're sure no email.
He did? Oh.
He did? Over that.
Yeah.
And just like.
Okay.
Is there extra credit on this? Excellent.
No.
So, someone should not have.
Yeah, there is no line.
It's like mentioned as a side note, but you don't really need to know what it is. So what about this do you want to go over? Sure. 1-3 conjugated systems. Stability, orbitals, reaction mechanisms. So, let's see. What's the best way to do this? These do kind of build off of each other. Okay, let me take a peek recording. No, it's still there.
Mormon, you would have got to. And also next time
Okay. So the this should be that's pi 2 star. Then in the pi 2 antibonding we have 2 flipped, and in the pi 1 star they're all. So remember that the phases, the way we color it, it's arbitrary. Oh, I have questions. Yes.
For pi 2, we also just have like 2 up and 2 down. Does it make a difference because
Yeah, we could do that.
2 in phase and 2 out of phase, or 1 out of phase.
So you're saying this, right?
Yeah, it doesn't make a difference, right? It's going the way true.
Not really. In fact, we should probably draw it like that anyway.
I was going to say, this is not important because those two have to bond.
They will, yes. Okay. Yes, I think. Do you have a question, Connor? Okay. It was Ethan.
That was my question. Don't the two that are next to each other, like the 2 on the left and the 2 on the right, need to be in phase?
Yeah, you're right. That's why they do need to be in that phase. Okay. So you've got to be careful. So remember with the nucleophile, it's the HOMO. It's the HOMO. And with the electrophile, it's the LUMO. So if we're going to go through a nucleophilic reaction with the pi conjugated system, we're going to be looking at this orbital right here. However, if it's receiving electrons, we would look at its LUMO. However, that's not likely to occur because if it's a LUMO, well, if it's acting as an electrophile, we have to jump into antibonding characteristics, and that's generally not a good thing. Unless it's just sitting there along for the ride for a very short amount of time. Okay. We've really only seen one reaction with this. And that is the addition. What?
Like the chain thing in the ring, or the mix the ring.
That's one of the reactions, but the specifically that I'm thinking about is the HCl addition, where we grab the proton, drop it off into chlorine. We make 2 possible products.
Another scary intermediate.
And then the chlorine simply adds onto there, or onto here, and we get these 2 species overall, like so. The reactions. So we'd use this as. So in this particular example, we didn't have to explain because I didn't ask why one is better than the other. But notice how this is a primary and this is a secondary. Because we generate 2 intermediates, 2 intermediates with different stability, we have the potential to make 2 distinct products. And this is where we get into kinetic versus thermodynamic. So the kinetic is the one with the more stable intermediate. Or we could argue the transition state, TS, whereas thermodynamics gives us the more stable product.
Which of those is the more stable? Oh, yeah, okay, sorry.
The only other reaction we've seen a lot of, or really maybe not so much, but for Diels-Alder to work, we have to have the 1,3 conjugated diene plus the just some alkene. So really this could be, so we could have, say, this for example, and we have like 7 other carbons attached to it, and we have, this would still work via a Diels-Alder. The basic thing we just need to recognize is that it's this section and this section of the 2 molecules. When you see that, you can that'll basically put you in like, oh, this is a Diels-Alder reaction. And in fact, looking at that specific thing via molecular orbital theory, I think it's one's the nucleophile and one's the electrophile. So I'll take, let me do this specifically. What am I trying to do? Nucleophile. So in the Diels-Alder reaction, the 1,3 conjugated system is the nucleophile. Yeah, and this one's the electrophile. So this is where it helps to look at the atomic orbitals to see exactly what's going on. So we look at the HOMO of the nucleophile as always, and that looks like this guy right here. So we've got 2 pointing up, pointing up, and that's the pi2 orbital. And if we compare it with the alkene molecular orbitals, it's just going to look like pi and then pi star, and then we have both in phase and then both out of phase, like so. So again, we're looking at the LUMO of the electrophile. Which one is that? Yep, it's pi star. So we line up the pi2 of the, I'll write HOMO down here, combine it with the LUMO of just the pi star, which comes from here. Is that possible to add across? It is indeed, because, look, these 2 are happening in phase, and these 2 are happening in phase. So if I pull these down, looking at a different angle, and then I take these 2 as well, I'm going to have to flip that. Flip. Or actually, I'll just draw it as is, but then we can. So we've got those 2, and then we flip that. So there we see that it's in phase and in phase. So we see because of that, that is able to occur via the concerted mechanism that we see. Simply because the two orbitals are in phase. Does that make sense?
And it's happening with the two outermost orbitals on the.
Yeah. I pulled those two and put them down here, and took these two and pulled them down there. And then I had to do the 180-degree flip so we could see how they line up. Well, so here they're not lining up.
Right.
In phase, out of phase, out of phase. But if we turn around, then they're in phase. So the molecule can take whatever. In any reaction you do, you can always reorient the molecule however you need to in order to attack or accept electrons. It's just got to make sense according to molecular orbital theory. Okay. And this, how many of you are planning to take the test today? How many tomorrow? I think, in addition to looking at my review, I need to look for, no, it's problem sets. I'm gonna like look through the problem sets and say like, oh, you should look at this one. Like, if you can work through this one, you'll be okay. How many of you are taking Monday? Okay. So let's talk about aromatics, aromatic reactions really quick. And so this is Q3 on the exam. So notice that most of these steps all of these reactions fall under electrophilic substitution. Does someone have a question?
Did we go over the question 2 step? We're going to go back to that.
I did.
So fire away, 'cause today I won't let the electrons burn my skin.
I did quite a bit in that. Yeah. Question 2, review. And question 4 is pretty easy too.
Notice how I said random.
Electrophilic substitution. Notice how we say electrophilic. Because remember that with the stability of the benzene ring, these electrons are so nice and cozy that we need something really strong, such as aluminum trichloride, in order to bring them out. In other words, for each of these electrophilic substitution reactions, we always need a comparatively strong Lewis acid. If we without that strong Lewis acid, there is no
Alert from Google Chrome.
substitution.
12 Agile Development Principles.
And so some of the reactions we've seen, either we start out with it, or we have to generate it. So the classic examples, either we start out with it or we regenerate it. And the classic example of those are Friedel-Crafts acylation and Friedel-Crafts alkylation. So Friedel-Crafts acylation is when we take this guy right here. So that's the acyl halide. As we've seen with its reactivity, it's already a really good Lewis acid. we can bring the carbonate up, reform it, bump off the chlorine. It's a good leaving group. And I'll simply make this. Whereas with the alkylation, for this, the first thing we really need to do is add an acid in there so we can convince this alkene to become a carbocation. Carbocations are also excellent Lewis acids. So that we can just swing right on in there, and eventually through the other steps in the reaction, we will get the product, we'll get that. So in each of these electrophilic substitution reactions, we're always going to lose aromaticity, and we're also going to regenerate aromaticity. This right here is the reason why the reaction goes forward. It's the driving force for the reaction. And I think what I should mention, don't forget that it's not just, you can of course do it with the straight up benzene ring, but don't forget about the importance of groups attached to the benzene ring. What do I mean by that? Well, we have the two types, electron withdrawing and electron donating. Remember that the withdrawing, so that even with these groups attached, it still follows the same mechanism as the other steps in the electrophilic aromatic substitution. But when you've got an electron withdrawing group attached on there, remember that we do it, it's OP directing.
Meta-directing.
It's OPD instead of OCD. And electron donating is M directing. Ortho, para, and meta. You guys know what the ortho, meta, para mean, right? Let's go over that right now. What? What? Sure. Like that? So O, M, and P mean it's going to... So O means it's on carbons 1 and 2, M means it's on carbons 1 and 3, and para means it's on carbons 1 and 4. So right here, this is ortho, ortho, meta, meta, and para. So with this as an electron withdrawing group, it's going to donate its new substituents to either the O positions or the 1P position. And the rationale to explain that is the resonance structures. The difference between what makes it ortho-para directing or simply meta-directing is the stability of the resonance structures, or the stability that the resonance structure shows in the intermediate. Make sense? What do you mean?
Just like an electron donating through.
Right here? This, or even phenol? Like that? That'll put its electrons into the ring, and then they'll just swing around like so. You will be asked to explain why it's OP or M, based on resonance. Okay. I think that's pretty good.
Excellent.
Any last questions anyone wants to ask before we wrap up? So again, oh.
Last question. Have you subscribed to my YouTube channel?